Bill for the EE599 project number 5 assignment. Today, I will be talking about FlowGNN, data flow architecture for real-time workload. So to start, I want to talk about the knowledge gap and the research goals. Advanced GNNs cannot be simplified as matrix multiplication and edge embeddings cannot be ignored. That's the main point of this section here. It's taken directly from the article. And moving on to the prior works. Previous work focused on prior work. Previous works were diverted to a specific class of graphic neural networks, resulting in a lack of generality. The majority of these GNNs are unsuitable for sparse matrix multiplication. And going to that many to one point, most GNNs handle one graph, while FlowGNN aims for many small graphs consecutively streamed in with low latency. So while previous works would focus on one stagnant graph, FlowGNNs aim to constantly compute and process multiple small graphs that are streamed in consecutively and have irregular patterns. Next are the real-time computation demands. This specific principle invalidates previous acceleration techniques, and such as optimizations relying on graph properties, such as graph preprocessing and graph partitioning. These are not feasible for real-time applications because you don't have access to the graph beforehand. It's streamed in real time. Next are the limitations. Accelerator innovation significantly lags novel GNN models. Furthermore, advanced GNNs cannot be simplified as matrix multiplications. Multi-dimensional edge features invalidate prior sparse and general matrix multiplication formulas. This is because redundancy through merging nodes with the same neighbors is invalid with edge embeddings, which goes into the last point, and edge embeddings invalidate optimization techniques. Next were the goals for the project. One of the big overarching goals were to fabricate a scalable data flow architecture that had expansive support for GNN models through a message passing mechanism, and they also wanted fast real-time GNN interface without pre-processing or graph-specific optimizations in order to meet that real-time requirement discussed earlier. They plan to do this through an explicit message passing mechanism. This includes message passing generality and multi-queue, multi-level parallelism for data flow architecture. This is for data flow architecture and performance improvements. Message passing can express almost all GNN architectures at the theoretical formulation level, and explicit message passing can easily integrate edge embeddings and different aggregations without changing fundamental architecture. Furthermore, multi-queue-based data flow architecture can effectively pipeline node transformation and edit edge embeddings, and these are the two most computation-intensive steps in a GNN with multiple levels of parallelism. Next is the architecture. The goal is to provide a real-time GNN acceleration architecture with great generality to support a wide range and emerging GNNs with minimum modifications. First up is the message passing mechanism itself. The message passing has two main features: gather, which is feature aggregation, and scatter, which is message transformation and passing. Edge embeddings are incorporated into the message during the scatter phase. Next is node transformation. It's a linear or multi-layer perceptron followed by a node update, and the method of computation flows from the gather stage to the node transformation stage to the scatter stage, and a global pooling layer is needed for graph level tasks, which can be followed by multi-layer perceptron layers for final predictions. Next is the data flow architecture. A node queue enables pipeline node transformation and message passing. Scatter and gather phases can be merged. This reduces process latency and memory cost. These greatly improve efficiency, specifically memory cost. And baseline data flow pipeline greatly reduces idle cycles. Non-pipeline incurs a large waste of idle cycles, and fixed pipeline suffers from imbalanced node transformation and message processing time. And here's a diagram of the previous slide. As you can see with fixed pipelining up here, it for node it has to the message passing line has to wait for the entire node transformation to finish before it can start processing. FlowGNN aims to have chunks of node transformation. When it finishes, it's sent to a queue of ready nodes, which is then sent to the message processing. And as a result, this skips this large waste portion right here. Next is the FlowGNN architecture and node edge parallelism. Multi-queue data flow for parallelized node transformation and message passing allows for the parallelization of message passing across multiple edges. Multi-queue data flow is based on instantiating multiple node transformation and message passing units. Each message passing unit processes its own bank of edges and reads and writes its own bank of node embeddings, and it achieves this through a node transformation to message processing adapter and on-the-fly multicasting. Through a node transformation to message passing adapter, it allows for the multicasting based on target node IDs, and each message passing will only process and scatter those edges and nodes. Next is the apply and scatter parallelism. FlowGNN node transformation uses two sequential processes. It uses accumulate, which reads aggregated messages and computes a fully connected layer, and output, where it performs finalization steps and sends it to the multicasting adapter. The node transformation unit controls how much of a node's message vector is read each cycle to update the output vector. The message passing unit, however, handles per edge computations. Moving on to the results section, our proposed baseline data flow architecture, along with pipelined node transformation / message processing within one node and multi-layered node transformation and message processing, are very effective in reducing the latency. First is the flow. Before we get into the results, I do want to talk about some limitations with the results. One of the competitors, IGCN, employed a redundancy removal techniques that limited IGCN's applicability to isotropic GNNs with no edge embeddings, and this isn't a fair comparison against Flow because Flow seeks a populace that directly sits outside of IGCN's capabilities. Furthermore, the main comparison with FlowGNN is the CPU and GPU using onboard measured performance as a metric. With that out of the way, we get to these two tables. This here is for the high energy physics, and this is for energy evaluation. As you can see, FlowGNN has a higher score amongst GPUs, which typically does better than CPUs. It shows remarkable speed up. This shows remarkable energy evaluation compared to CPUs and GPUs, which is evidence that they did not that in their search for generality, they did not sacrifice performance. Next are the data architectures. This is the effectiveness of the data architecture. There's fixed and pipeline, and there's fixed pipeline and non-pipeline, and these are the competitors between them. Furthermore, there was an abolition study that revealed that the speed up for FlowGNN is nonlinear. This is due to the entangled effect of the This is due to an entangled effect between the apply, scatter, and gather transformations talked about previously. Depending on which of these is the bottleneck, that determines what aspect needs to be increased for speed up. So, for example, if you have that message processing is the bottleneck, but you increase the processing power of node transformation, you don't see an increase because you're making something better that isn't the holdup. Message processing is the holdup, and that's why if you increase node transformation, you will eventually saturate the message processing unit, and as a result, you will not get any more speed up past that. Furthermore, another possible option for why speed up is nonlinear is that imbalanced message the imbalanced message passing workload due to imbalanced graphs could also have played effect in the speed up aspects. This concludes the presentation for EE 599, presentation number 5 assignment. Thank you for your time.